Slide and a new request. Okay. So we continue in last week. Okay, let's get analysis. So for the cascade analysis, we stop at here. However, the table here is not complete. But to understand this table, we need to understand this table. We need to refer to another papers. By Manan et al. 2004. This paper number 2. Okay? I simplify it. A slide. You may refer to slide 2. Slide 2. So what the cascade analysis? This is under slide 2. But the paper itself is targeting the minimum flow rate. Targeting the minimum water flow rate using water cascade analysis technique by Professor Zainuddin in 2004. So this slide is based on this paper. So water cascade analysis is a new technique at the time in 2004 to establish the minimum water wastewater target for continuous water using processes. The WCA is chemical alternative to the graphical water targeting technique known as the water surplus diagram. By eliminating the tedious iterative step of the water surplus diagram, the WCA can quickly yield accurate minimum water targets, pinch point location, and water allocation target for a maximum water recovery, and thereby offering a true complementary role to the water surplus diagram. This is water network. Last week we learned about mass transfer and non-mass transfer based operation, but it's not limited to mass transfer based operation. It's applicable to a wide range of water using operation. Although in this case, it's a water cascade analysis. Figure one is figure 7 in the paper. Shows the process flow diagram of acrylonitrine and is produced by the vapor phase oxidation of propylene. So here we have propylene and ammonia of propylene detectors in a fluidized bed reactor at 450 degrees at 2 atm according to the following equation. C3 is propylene ammonia with oxygen, excess oxygen, and catalyst produce the ammonia, sorry, acrylonitrile with water. So we have this exchange that goes to the scrubber, we can goes to the distillation column. Mm, sure, what is this? Check. FW is boiler frequent. Okay. So boiler is student including the gases. So this is a single pass selection with almost no version of providing the product of the wool and condense. The vector object is sent to a scrubber and uses fresh water as the scrubbing agent. The bottom product vector as the scrubbing agent. The bottom the product of the scrubbing is inserted into the first layer and organic layer in the decanter. The layer is perfection with solution column. So there are two water demand for this process. The boiler feed water here. The water feed stream to the scrubber to the river. So we have water demand and water source. So demand is inlet, water source is outlet. There are the source that include the obvious condensate here. 1, 2, 3, 4. Okay. The aqueous layer from the decanter distillation bottom and percent on the steam jet ejector of gas condensate is here. So all of this water source going straight to the wastewater treatment. Ammonia. Ammonia is the main convenient in this process. The water source are regarded as wastewater and sand biotreatment facility project. One way to the bottleneck recycling, however, only from construction must constraint imposed on the water demand sources as listed below. So right now we are doing the cascading after this to identify what is the pinch for this system. Probably we can either reuse or recycle the water, but despite of the that we need to meet the requirement for the scrubber flow rate of wash feed between 5.8 to 2 kg per second, while ammonia content of wash feed is between 10 ppm. For the polyfeed water, BFW decanter in the distillation column. This is the question. They keep some tolerance. So we work around the tolerance. The first step in establishing the minimum water target is to identify mm, define the limiting the data process subject to change this level. The data of the flow listed was drained first, which involve the stream selected for water reuse. Consider because only two is the demand. Water reuse goes either the one. The first constraint requires the flow rate and the concentration of the scrubber wash it to be bounded within the given range. Thus, to maximize water reuse, one should maximize the ammonia concentration while keeping the flow rate of this water demand to a minimum. The second constraint means that only pure water should be used at the as the VFW constraint. Constraint for BFW, there will be no AN content, there will be no ammonia content. Okay. So the BFW is must use pure water based on the constraint. The limiting data for the water demand, water source are summarized in table 1. The water demand BFW 1.2, scrubber 5.8 with 30 ppm. So for the scrubber, the highest concentration for ammonia in the wash feed here must not exceed ppm. Yeah, 10 ppm. Yes. For the water source, the flow rate here, oh sorry, the flow rate from this table is coming from here. It's be the 1.2. Not sure why it's flapping it. It's clearly, let me check the constraint. Oh, 5.8 because it's using the minimum because in the constraint in for the scrubber, the flow rate or the wash rate is between 5.8 to 6.2. So we choose the minimum. For the consideration we use next equal. Next is for the water source. So for the water source, this is in bottom here. The flow rate is 0.8. 0.8 with column 0.8, yes. Oh, okay. There are no constraint for the bottom distillation column. For the distillation column, the constraint is is for the feed. But from here we can see the data. No ammonia is going to the bottom. All of it is to the as a top product. So 0.8 is KGAN or KGH2. So since there are no concentration of ammonia, 0 ppm, because ammonia is it's based on our this concentration. It's based on the ammonia. We often get condensate from here. We have how much? 5. Yeah, 5. Is there any constraint? No constraint. So 5, 5 is and 40 ppm for the concentration. So what we need to do when you see the question, you need to identify the water demand, otherwise sometimes the question explain to you already what is the water demand. or describe, sorry, describe which one, which unit, unit operation that require water demand and what is the water source. So for the water source, it's normally easily easily identify if that stream goes to the wastewater. So meaning the source for the wastewater is normally is the water source. So our target is to reduce the water source. So by reuse or recycling it, so that we can reuse the water demand by replacing it with the water source. What is aqueous layer for the decanter? Decanter. Okay. So for the decanter here, 25 ppm with 5.9 ejector condensate for the boiler here before 1.4. Okay, okay. Now that we have identified which one is the demand, which one is the water source, then we can, okay, we can do the water cascade analysis. So what we need to do before we do the water cascade analysis, we need to identify this two first, very important. Then for the water cascade analysis technique, here's the guideline. A good tool should satisfy three basic requirements as follow. You should be capable of handling both masters for best and non-masters for best motor operator operation. You should consider the flow rate and the concentration driving force for water use. And it should be non-iterative. Thus can quickly yield the exact target. So the main objective of the water gas is to establish the target. That is the overall freshwater requirement and wastewater generation system. After looking at the possibility of using the network sources within the process to meet the demand. So the keyword is water sources. We using it back either by reuse or recycle to meet the water demand. So before the water cascade analysis, the water demand normally it's a fresh water or water with some contaminant inside, but mostly it's clean water. To achieve this objective, one has to establish the net water flow rate as well as the water surplus and deficit at the different water purity level within the process under study. The first step in the WCA is to set up the interval water balance to determine the net water sources or water demand at each purity level. The first column of table 2, this is the, yeah. You can refer to the paper by Manan 2004. So in table 2, the contaminant oxidation level arranged in ascending order. So since based on the table for water demand and water source, we have six sources. Can refer to the paper, 6 sources to make sure. Then from the 6 sources, we arrange it ascending order from 0. If you see the table, the concentration start from 0 until 34 ppm. But for 0 ppm, especially there are 2 sources, either from the BFW, the water demand, or the water sources from the distillation bottom. Both trading a similar concentration at 0 ppm. So from 0 to 34 is from the table of limiting water data, table 1. Number 6 here is the highest concentration, which is near. For the ppm, highest concentration is 1 million. Based on the question 2 in this Manan papers. So for the water cascade analysis, you need to do these 2 first. Kita ada ini level and the pressure in ascending order. Okay. So its concentration level is expressed in terms of the purity in the second column with the concentration of pure 1% at 1 million pp. The fraction of pure water in concentrated stream or the water purity can be expressed as P equal to 1 million minus C over 1 million. 1 million minus C over 1 million. So C is from column 1. Column 1. Column 1. But this one is only label. Label is just for the naming C1, B1. So how to calculate this? So you have 1 million minus 0 over 1 million. So 0 is coming from here. So 1 million minus, in this case, 0 over 1 million is equal to what? How about this one? Bring your calculator, turn it on, and see. 1 million value minus 456 minus 0. Minus 10 divided by 1 million. 56 okay. 0.999. And you do it so on. And for here, 0 1 million minus 1 million is 0 divided by 1 million is equal to 0. The water purity difference P here, what? Not delta P for pressure is for P level. Interval K, it's interval meaning between the K. So this is 1 and 2K. So 0.01 is between these two in the middle. So how to calculate this is just easy. So 1 minus 0.99999. Then you get 0.0001, 2, 3, 4, 0. 0.00001. The same thing for this. 0.99999 minus 9999 at 6. Get 0.0. So that is for the column 3. For the column 4 and 5. Total flow rate for the water demand and water source at their corresponding purity level. The flow rate of water demand is fixed as negative and water source is positive. So for FDJ, FSI, this is for flow rate. For the demand, D, S is the source. So for the demand, the value is negative. So where do you get this value? Is from the table 1, limiting data. So for the limiting data, refer to table 1. For the 0 ppm, we have two value, 1.2 and 0.8. So for the 1.2, this is for the water source, sorry, water demand. For the 0.8, it's from the water source. See the water demand for the 10 ppm. Is 0.58 from the water demand number 2 there. Trouble. So the rest is the water source. So this value 1, 2, 3 is related to the purity. 1, 2, 3 with the purity. For 4 and 5 is related to the flow rate. So flow rate, where do you get the value? From the table limiting water data. So that will limiting water data coming from where? From the from the figure 7 or the process. This flow rate sum up at every purity level to give the The flow rate are summed up at each purity level to give the net interval water flow rate. FDJ plus FSF column 6. So plus represent water source, minus demand. So this one you sum up here, 4. Okay, and relation. Then 7 need to identify which one is demand and the source. So once we're done with the interval water balance table, next is the water cascade. Water cascade figure 10. For the water cascade, see here priority K. So priority K here refer to the column 2 for table 2. The priority PK. So K is referred to the level. So P1 is 1 with the C1 equal to 0 ppm and so on until P5. So the P6 here it's P6 is pretty 0 because the concentration CK is 1 million. The one is the maximum. Then between the P, there are delta P. So delta P refer to the column 3, to the interval water balance. Actually, it's a minus between P1 and P2. This one is between P2 minus P3. Then you get all are available in the table water balance table. Next is the water cascade. So for the water cascade, we start with the fresh water at 0. So FFW refer to the fresh water, 0 kg per second. Then the cascading refer to the column 6, minus 4, 8, 5, 5.9, 1.4. Then this FWW is equal to the wastewater. Flow rate for the wastewater. Cumulative water source and demand. That's it. Do one by one. The next step in evolution A is to switch the freshwater and water target for the process. In doing so, it's important to consider profitable both the both the water flow rate, balance, and the concentration. The reverse water quality ensure that the true minimum water target will be obtained. The water flow balance, flow rate balance involves using the water cascade diagram, the 10, to obtain the cumulative net water source or demand for a process of C. This is C. This one, last week, um, explain why we need to do this is to reduce the amount of wastewater generated and to reduce the freshwater use. So if you refer to this, you can cut the freshwater use by 50% and reducing the wastewater by 50% by reusing the water. So for the water cascade diagram in figure 10a, freshwater flow rate per second is the same. Yes, we start at 0. Here the net water demand is 10 kg. Okay, what we'll do. This currently water demand means only net water sources down the next 3 will get that to the source of wastewater flow rate of 6.1 kg per second at the lowest quality level of water cascade diagram. So this is the sum up all of this. Then you get the 6.1. In addition to considering the water flow rate balance, the true minimum target can be realized only by also taking account the pure water plus deficit, which is the product of the cumulative net water source or demand FC and the pretty different delta P across two pretty level figure 10P. Okay. The pure water surplus means the sign, the positive sign, means the water is available with purity higher than what is required in this region. The pure water deficit negative sign means that water of higher purity than that available is required. So here for the cumulative water source demand, here 0.4, then this 0.4, because this is 0, 0 plus -4, -4, -4 plus -5.8, -6.2. 6.2 plus 5, 1 plus 5.7 plus 0.7 plus 1.4, you get the root 6.1. Good. What of you want to subtract the deficit is square 0.0004 is the product of the product. Product means would multiplication. This one multiply with delta P. This one 0.4, sorry, 0.4 multiply with delta P. Not this one. So 0.4 multiplied with this, we get negative 0.00004. The name what 0. The same thing like for this 0.0008. 6.2 multiplied by 0.000 will be 0, 1, 2, 3, 4, 5. So you get 0.0000 ada 40, 248. The same thing for this here, what is the cascade? Then you do cumulative pure water surplus. So cascading, this is the cascading. Because 0.4, yeah, cascading, this is plus this one, then you get this one, plus this one, this one. Okay, so on. The other one is the cumulative pure water surplus. Notice that for the pure water cascade in figure figure 10b, cumulative pure water deficit observed from second to fourth level, P2, P3, and P4. The deficit on the pure water cascade indicate that the pure water cascade is invisible. So P2, P3, P4, so the interval freshwater demand this one is still, does it mean there is insufficient freshwater in the network? Does it means there is insufficient freshwater in the network? Zero freshwater flow rate during water cascading. Even when we start the water cascade analysis, we did set this to 0. But it's enough, no deficit. Additional freshwater should be supplied to remove all pure water deficit and yield a physical pure water cascade. So the highest of pure waters to be supplied at the highest purity level here. To minimize freshwater, it is necessary to determine the minimum flow rate of fresh water or the level freshwater demand that will satisfy the total water requirement at each purity level. Interval fresh water demand will restore a feasible pure water cascade throughout the entire water network. Figure 10C shows that interval freshwater demand FWK. So this K refers to the level. FW is the freshwater demand. H level K is obtained by dividing the cumulative pure water surplus by the purity difference between the fresh water supply and purity level PK of interest as follows. I think that cumulative pure surplus this value between either pretty different between the water supply sea level decay of interest. So 0 8 0 and 0 0 0 0 0 0 0 0 impact. Oh, and cool higher. Yeah, turns out that's the key. So, that, so 1 minus 0, right? 999 99986. And so for this, calculation, into 20 what is plus divided by this value minus this value. Coincidentally, it's delta P for the first purity level, but for the second purity level, actually this value to 1. Number 2 is between 1 here minus number 3. This value divided by 1 minus 3. 1 minus 3 is P1 1.0000 plus then 6 degrees. Yes. Right, right. 6. How about it's one? It's a PFW purity for the fresh water is 1. 0 ppm. 1 minus how much is this? In 9.5 and the rest hour. Referring to figure 10C, a negative value for WK means that there is insufficient fresh water, whereas a positive FWK means that there is excess fresh water at WK level K. To ensure that there is a sufficient fresh water at all points in the network, fresh water flow rate of ZT the same magnitude of as the absolute value. So the largest negative WK should be supplied at the highest purity level of the visible cascade. Figure 2. So you see it. So the water FWK should be applied with the highest level. So from here we found that the pinch, the highest, but the fresh water supply is very negative 0.57 kg per second. So this value goes to here, like this. So same ways, chosen one to recalculate back, not for the purity. This is the same. This is the same, except for this. Where you get this value from the I don't know what to call it. Interval water balance table, table 2. But for the cumulative or cascading, recalculate because we have new value for the FFW. So 2.057 minus 0.4, then we get this value. 1.657 minus 5.8 or plus negative 5.8. Negative 4.143 plus 5. until you get the FSW. So you see the value for FOS water is increasing when we increase the fresh water for the filter. Next is to do the pure water surplus deficit. So how to calculate pure water surplus deficit? So to calculate pure water surplus deficit, we refer to mm, video. Pure water surplus deficit is the product equation implication of the source of demand. The delta. So this value here is so this value here is the motive FC with delta B. The same for this value and with delta B. Next is to do the cascading for the cumulative pure water surplus. Plus 0.0016 8 with the pitch. It will be at P3. Is it P3? See? P3. P3 levels. Why is the pitch? This is the highest demand of negative 2 kg per second. Actual demand, which we choose as the the fit as the required measurement for this system. Yes. Which is just cascading class. So the physical water cascade will I think we stop for 3 minutes to go through first thing and cumulative water supply. is boring. Continue. So continue. So the visible water cascade yields the true minimum fresh water in the wastewater flow rate W and FWW. For this value and this value. At the third predictable P3, yeah, there is a zero cumulative pure water surplus. Is the pinch for the AN problem. The pinch is the most constrained part of the network to result in maximum water recovery. Sorry, this is the water cascade level, the value CP for AN production case study. So this is the complete water cascade table. Here we have six well, the concentration start from 0 to 34. The 1 million is the maximum. And the purity we obtain this from the equation 2. Yeah, equation 2. Start from equation 2. So for the purity PK equation 2, which is this equation, this is equation 2. 1 million minus 3 over 1 million. FDJ is sum of low demand. These two values, this value is coming from interval water balance or the limiting water data for table 1. So these two demand and source is coming from this. It's from the process. This is the summation 0.1.2 plus 0.8. Then we have the FC. So for FC started at 0, and we started calculating to identify the maximum. So the maximum required fresh water is 2.06. Simplify this value. Yeah. Until to here. So from the first column until the end, we already discussed everyone of it. Yes. Through WCT, the WCA technique offers two other key advantages over what is a cluster in enabling the minimum targets. Apart from it, to eliminate tedious administrative step, yeah, what the surplus diagram typically yield the exact productivity target in the pinch notation. The first, there are some iterative, but only once you identify pinch of the, the, the minimum freshwater required, which will be depending further to W. If it's considered an iteration, then it's only one step. First, the advantage is that we get the of the minimum freshwater and wastewater in the cumulative net water source. So, one the second advantage using water gas table that is designer to clearly identify the pinch causing stream exact water location region above and below the pinch to achieve the minimum water targets during the design. Referring to table 3, is table zero cumulative pure water surplus at the purity level 10996 will present the pinch point. Note that the pinch causing stream which exists in this purity level the flow rate of 5 second is 1. Referring to table 1, this stream is a single water source is of this condensate. We refer back to the figure. The off gas condensate is just after the reactor. So the figure 7 paper. Uh, exercise. Exercise. What the you say analysis of the time giving? When you do this, yes. So for this, I changed the t-shirt, the flow rate. You do this, yeah. The second of the exam method, how to use the water cascade table for the to identify the pinch. First thing you need to do is preparing the interval water balance table. Table water balance table you can refer to table. So in table 2, there are 7 columns that you need to do. You need to calculate, you need to prepare. First one is the level. This we have 6. 1 is only for this case. Yes, 6, still 6. Because the concentration is the same. You see 0 concentration here. Then the purity pK, this one you need to use equation 2 from the table. If you have any question, ask later or through email can as well. Now we continue the we finish with the water cascade, but next week we'll go to the case study by case study, including case study for gas. So next week we have class on Saturday. This is what we have learned just now. Yes, on Manan paper number 2, Manan 2004. Next, sourcing composition. So the sourcing composition is another method used to target the new stage of fresh resources for recycled or the use the book. Okay. Five step constructing the water system. Sensors composite curve. So you have learned about water source, water demand, or sink. Mm. So if you refer to see the demand in the source. So what for your case from that information you need to plot it on plot, plot it, spread the same descending order of dividend consumption. So the mass load refer to the PM. Rank the sources, seeing the sources in ascending order. So for the number three here, the first number one and number two is not before shifting source proposition. So not it. So it should be central. Next is super meaning shift the signal. So shift the signal before the source, and there are some point here in which the source and the signal found a tangent, which is the pinch point for the process. The way we, in order to do this, you need to show how to do it manually. Think on transparent paper, transparent plastic cans. In order to superimpose it, meaning is draw different page, and we suppose we see at which point it's set. The sources for the sourcing compared to what the cascade analysis, you need to do some calculation, but the calculation is not that hard. Yeah. If you use Excel to do the example, then it's just give you easily done it. But for the test, it's yeah, you need to do some calculation manually. So the fresh water target is the for it saying which manner side the medium which the direction target is for it. So this is the required fresh water. This is the required. It's the same for the water cascade analysis. You also get this value. Yes. If you choose to do the Manan 2004 based on their data for this method, you get the similar value plus minus for the fresh water and wastewater feed. Then process modification. For process modification, can also refer to Paper by Manan, paper number 2. Okay, page 3178. So for the process solution, actually, modify either the product. So step to modify the process and measure the water source in fit to the which process. You can list how you determine the pinch either through graphic like this, the same composite curve, the same source composite curve, or through water cascade analysis. So for the water cascade analysis, you see the pinch. They are below and above the pinch is the same for this case. Below and above the pinch. So for the above the pinch, beneficial changes can be checked by either increasing the flow rate or the purity of source, or by decreasing the flow rate or the purity requirement of the sink. These changes will have the effect of increasing the water surplus above the pinch, and thus the amount of the water barrier will be reduced. The same thing for the paper. Go to the paper page 3179. Regeneration above the pinch. Water source in the region above the pinch are partially treated to upgrade its purity. Next is the below the pinch. There is already a surplus of water below the pinch. Any flow rate changes may will affect the target. An exception to this rule of thumb is for the case where solubility is increased, so it moves to the region of the pitch is and at the pinch point using the breadth of the source at the pinch concentration did not reduce the target. If you refer to the paper, it's talking about regeneration. So talking about regeneration, meaning the water source, in this case, it must be treated by using a regeneration. It must be treated to a certain concentration, certain purity level, which allow it to be used for the sink. Not that for the paper, not that the regeneration above and across the pinch, meaning here or on the pinch itself, will reduce the freshwater consumption and wastewater generation. Whereas regeneration below the pinch here will only reduce the wastewater generation. Could that only two possible scope process pollution to further reduce the water target. Enhance water consumption has been explored. These are water regeneration and equipment modification. For the equipment hardware modification, modified in order to reduce water utilization. Water emission only involve emitting one of the water sink. Water water reduction is changing the percentage of water process. Right. Next is the water regeneration. So for the water regeneration involve the partial or total upgrading of water purity, purification, techniques such as filtration, gravity settling, activated carbon membranes, biological treatment. So regenerated water source will have a higher water quality. Regeneration techniques used in the solution. For example, filtration will be essential before a membrane to prevent membrane falling. So, okay, this one, this is from the paper. Yes. Use of water composite curve and the pH property essentially water composite curve. So, slash water cascade table slash sink and source composite curve. And the pH related to guide the regeneration of water sources as follow. Regeneration above the pin water sources in the region above the pinch treated to affect water purity. Regeneration across the page region below the page shown to higher depth of page purity. As a regeneration, so regeneration above the page will reduce the fresh water need. Yeah. If you for the across the pinch, you need to regenerate it at least higher than the pinch purity because pinch purity there's a level. Last time we do a we based on Manan 2004, it's purity level 3, then we regenerate it above purity level 3. Regeneration below the pinch. So for the below the pinch water source in the region below the pinch partially treated, but the thing is, although we regenerate the water below the pinch, it's still not up to that pinch purity level. So by doing that, we can only reach amount of wastewater regeneration. That's the point. The freshwater consumption will be the same if you to regenerate the water below the pinch. So the the thing is we do this analysis is to identify that Yes. Done. Now is the water network design or retrofit. For the latter, what is the step 4? Go to the books. Chap. If you want to know more, the book is not, it's not enough. You need to refer to the actual paper that they refer to in order to understand how the design and the retrofit. Okay. For what? For water recovery network, there are three important heuristics. What fit water sources above the base? Distinct voltage balance. It has to be noted that in order to achieve freshwater and wastewater flow rate target, it is necessary to observe the pitch division. So this is the this is rule of thumb. See, the water sources above the pitch may not fit sink below the pitch and may not sources that are below the pitch must exceed the pitch. Vice versa. So do not fit sources above the pitch to the sink because the way why we do the pitch analysis, we need to identify which sources, water source that can be recycled or reused. Where? To the sink. So if the pit water sources is above the pinch, so we cannot use that water for the sink below the. That's all. But normally the sink is below the pinch. Sorry. The pinch is above the sink or water demand still the same. Similar. Normally it's above the pinch. Let's say some of the water source at purity level above the pinch, so that purity level above the pinch must not be used to feed the water source above the pinch. Let's stick to start the sourcing measurement success with the sink at the lowest contaminant concentration. So all the sink and sources in separated. So this one sourcing matching process. We stick on two. Proof of thumb number 2. You remember the the sourcing composite curve, it started at 0. The same for the water cascade table. The fit for the flow rate for the fresh water is started at 0 kg per second. Once we identify the pinch, then we can use the, the maximum, sorry, the minimum fresh water needed based on the pinch point as the fresh water flow rate. So for the second characteristic must be started at 0. The same thing for the diagram before you do the shifting. Heuristic 3. Map the reservoir source 1 to the other and fresh water is required, which sing according to of quality. Oh, measure source 1 and until all things Simanan 2005. Oh, Permanent 2005. This one no sure. Now is the sourcing positive page 371. Another way sourcing can be used to show the water relation or design between the source and sink. In constructing a sourcing check over the curve, again, zero yes, no. Step 1 ada 5 step. Oh, following step, not 5 step, 2 step. Satisfy a sink using the water sources. If the sink waste load is met but not the fluoride, fresh water. For example, figure 10.12 sink 1 SK1. Fluoride can be satisfied as by part so 1 RO. So by fresh water fluoride of SW SK1. The mesh load is fulfilled by MSR1 SK1 and the MFW It's for fresh water. Exactly what? Saying what? Over here. Yes. And part source two start here, and the fresh water after WSK2. Here, started at this source or SK1 until SK2. The procedure is repeated until all sink have been satisfied by the river source and fresh water. The master location for each sink is shown on the y-axis the graph. The polar location is presented axis. Hmm. Ini dapatkan nggak jadi Jawa terakhir? Jadi, hmm, yeah, actually, once you understand the water cascade analysis, this is same. Yeah, that's how method to choose. At the end, you want to know, like, where is the pitch? So, where's what the pitch? We can identify which one. The sources can be was to which things. Let's not revisit this. Let's certify the must not tolerate seeing using the penis as well as region and make sure the community target are satisfied using the notification again. Just start this. Studies in the book. Study for this network allocation diagram. So that's all. Nation based on the book is based on the payback period. Years to capital investment divided by annual saving. So you see the unit investment is in dollar. So dollar per year divided the value within years. Good period. Not playback period. So payback period. Yes. For primary calculation of paper is already processed separately on tester we have a solution. The credit is calculated using equation 10.7. The net capital investment is the investment needed for farming out the farming established with process consistent. The net annual saving is the one of the investment. So the net annual saving is from the freshwater can be reduced by reducing the freshwater usage. Then there's a saving. Well, what is the program? There's a small check this show. Okay. 22. A. Create limiting CC. So limiting CC equal to limiting commodity cost or limiting CC against the limit M. So M in M not in kg per hour. Calculate the minimum calculate for maximum reuse. So this is LCC. Another method or many method. But in the end, it's the same. Yep. From this table, you can also do the water cascade analysis of the table. So from here, you have got it 0 to 100, 0 to 100. Another question is 50 to 100. One is 50 to 100. That's what is. Next way. Oh, yes. So from here, you combine it. You combine this. You follow the red or the red line. So this red line is the political, the combined emitting water profile. So from here you draw the minimum water supply line with the minimum heat time. So this water supply line, the point where it's intersect the composite curve is equal to the page. In this case, page point is 9 kg per hour, 100. Okay. So the first question here is to draw the LCC. The second question is to calculate the minimum. minimum flow. So we from this, we know already that's on the pinch 9 kg per hour divided by 100%. This is just unit conversion to ton per hour. This is for the CC exercise. So you have two exercises to do. First exercise is for the water cascade. The second exercise is for the LCC. I need to do it next week. We will go for the case study, but the case study we limit it for the uh, for for the cascade method. As you see, we are plotting permanent versus permanent interval. Minimum water flow rate from maximum. So first thing need to do is thing you need to do is to plot the C and C out. Yeah, in the graph. So meaning you have 4 arrow, 0 to 50, 0 to 50, 500. Once you get the arrow, then you need to combine it. Yeah, hitting positive. So once you draw the limiting composite curve, then from the 0, draw a water supply line. Make sure check the composite curve. This point is the pinch at 14 kg per hour. So the minimum water flow rate using this method for 14 kg per hour or 14,000 per hour, but 50 ppm. This one is done. Wait, Yeah. Hello. Thank you. Sorry. Just to show you the case study, the books. Here. Okay. So this is the case study, successful case study in social education. The PPA has included this description of about operation such as semiconductor, so the chlorine, petroleum palm oil, refinery, and this example of the application of WPA on higher petroleum case study described by Morel, Win, and Aliwadi. This illustrates the next. This is paper in 1999. This is the tire petroleum process. So the scale tire are liquid fuel via pyrolysis. So meaning this process is not yet new to convert the rubber to liquid fuel. It's 1990. This is based on the actual process. Okay. The tire goes to the water shredding. The shredded tire go to the reactor. So from here, there's a water. This is just a shredded tire. So the water needs to go to the filtration. So from the filtration, I'm not sure what is the filtration. There's a cake, wet cake, solid waste handling, meaning from the filtration, the wet cake is forming on top of it. Then you get the fresh water. Not sure what is the compression, but this water is applied back to the water jet trading. So from the pyrolysis reactor, you get liquid oil and the gases. The gases goes to the condenser. This is the gaseous fuel. For the condenser, this is a liquid form. Liquid form, they use the decanter to separate the two water at different density. And some goes to the water with the oil, goes to the wastewater, the light oil, the skim it, goes to the separation, mix with the liquid oil, do the separation and finishing. Not sure what is the finishing, but here you get the liquid fuel. This is the water. Oh, okay. So the water demand is here. Fresh water goes after the filtration mixed with the filtrate regenerated. This is a regeneration. Regenerated water or filtered water mixed with the fresh water goes back to the water change trading higher. Here there's another fresh water still pot. So what is the still pot and clay? One goes to the next one. So limiting water data for the fuel to fuel case study Sing 1, Sing 2, or the value. Yes, there are values as to what for the source. You can see. Yes, two. Yes, to source to sink. So for the sink, water jet makeup and the seal pot with water. This is the information. SR1, SR2, source 1, source 2 is for the seal pot wastewater and the decanter wastewater. Transfer this information to the waste load versus flow rate. So mass load here is mg per second. So here need to change the unit per second. This one is kg per second. Is it kg? Okay, this is kg per second. So the first thing you need to do is to load it first. Then you shift it. Load its individual, meaning it will not intercept between source and sink. Then you shift it so that it overlap. Then you can identify the freshwater needed and the wastewater generated here. Oh, it's here. It's here. So from there, copy. Refer to book, immediately. So the fresh water needed is minimum fresh water. So this one is for the SK1 and fresh water. Then we have source 1 is 0. So here this line, this is 0.05. SR1 for the 2 is R1 and the SK2 is 1 and SK2. Source 1 in the sink 2. Next is the SR2. R2 is for the sink 2 and the wastewater treatment, and source 2. Ada satu. Source 1 and source 2. One is source 1, source 2. So this value is the it's between this point. Yeah, this value 0.45 0.045, 0.055 is yes on this point. So from there, to identify the sourcing temperature curve and the network allocation diagram NAD. Then we can come out with the another diagram with the water recovery. If you refer to the first graph, first flow rate here, first process. Refer to the first process. It's using fresh water. Now after the water recovery, we are reusing the water. So from here, decanter is here. Here the wastewater is going to the wastewater treatment. For this case, the decanter goes to the clay. Some of the water goes to the seal pot. From the seal pot, divide to 2, 0.05 goes to the seal pot again, mix with the water from the decanter, some of it going to the clay. Okay. Then part of this water goes back to the filtration. We reduce the fresh water 0.135. Before this, fresh water needed is table. Fresh water 0.28. 0.28. This one is only 0.135. So the value 0.045, 0.055, 0.45, 0.155 is based on the NAD network allocation diagram. So source 1 goes to the source 1 and SK2. Source 1 is source 1. Source 1 is the seal pot. Seal pot is here. So source 1 goes to the 0.45 goes to the sink 2. Sink 2 is the seal pot. Okay, valid. Goes here. Goes back. Scene 1 is the water jet. So scene 1 water jet. Aku sahut cara. So this goes to source 1. But it's but we do this. We need to. Why we do this? We want to know the source 1 goes to which part. So in this case, source 1 will be redirected because source 1 is water, redirected to going back to the source 1, and some of it goes to the another one goes to the source 1, then it's going back to itself, which is the source 2. This one. This is the source one goes to the source one and escape two. So escape two is the cell port. Oh, voilà. Goes back. Hmm. Voilà. Ah. Oh, not SK2, SK1. Oh, I see here. The 0.005 goes to the SK1. Dia punya graph tu, dia punya kotak tu lebih jauh sikit panjang. So this one goes to SK1. Look at SK1 goes to itself lah, I think. Think that's all. Yeah. So what you have learned today is what the cascade table, get the pins, sourcing allocation, sourcing curve, get the pinch, sourcing allocation curve, uh, and couple with the network allocation diagram to do the water network or retrofit based on this lah. Then you get this one, meaning the water, mm, mm, the water requirement, the water requirement will be reduced because you are reusing the water back either to itself. Based on, if you refer to this, is going back to the seal pot, some of it goes to the filtration, but there's some added water here. Instead of using 0.28 kg per second water, we now reduce it by, yeah, we can say by half, 0.135 kg per second. All right. Hopefully you learn something. Those haven't, right? Um, uh, those who haven't check in. Or you can contact me anytime if you have any question regarding the subject. So what you have learned actually can be implemented if you're working in plant. It's possible to do the optimization for the water in the plant, way to get the fresh water, actually how to reduce the fresh water and where to get the water reuse, water regeneration within the plant itself. So thank you.